Thank you. Thank you, everyone who is here. So I've been taught how to say buenas tardes. That's as far as I can go in Spanish. The rest is going to be in English. Apologize. Yeah, so I'm a compute specialist at AWS. I work with a lot of customers in different industries, usually tend to be around large scale compute, which is where the talk is coming from. And also all of the learnings from running such large scale compute on different types of either EC2, so our compute service, but also EKS, ECS, etc. I'm also part of the technical oversight committee at Finos, which is a sister foundation at CNCF. So that's also where part of my background is in financial services. So we're going to talk about why would you run your compute on Kubernetes, in addition or above the silver bullet kind of attitude that the community has of we're going to run everything on Kubernetes. On top of that, above all of the hype, there is also a good amount of things that come for free by using something like Kubernetes, and we'll look at all the different aspects that this affects your workloads. Part of those learnings are also from my previous job, where I was the architect for one of the biggest banks, and we actually deployed the first large-scale Kubernetes clusters for HPC workloads. So before I start, how many of you actually know what HPC is? 3. Okay, so HPC stands for High Performance Compute, and it's actually the name that is given to really large-scale compute clusters that do some sort of calculations. So we'll look at what that is. We will also look at, how do you run this, but also what do you need to change to be able to handle. So I have a question for the audience. What do you think? What's the largest scale? That doesn't include you. What's the largest scale compute can go? Like, how big can a Kubernetes cluster grow? I know of the previous talk, but she did not actually talk about the actual sizes, but sure. 110, yes? Correct. That is correct. So the actual official limit that the Kubernetes website lists, and they have actually done some testing on CNCF to do this, is about 5,000 worker nodes. It's 110 pods per node, and it can go as far as 150,000 pods per cluster. That's the official limits that we publish as Kubernetes community today. I can tell you that it can be pushed further than this, but it tends to be more around managed services. So one of the limits that the colleague before spoke about is actually the size limitation of etcd. It has a size limit of 8 gigabytes. It cannot go further. Then every single object, every single version of every object is stored there, which is where this limitation actually comes from. So we will actually look at how do we, either fix, reach, or break those limits. So again, just getting everybody in the audience on the same level of understanding. HPC tends to have 2 different types of workloads, and they affect how the scheduling works, but also how the rest of the communications, processing and inter-process stuff works. So between those, we have loosely coupled, which is more so in the financial services world. This is where you can run what I call a very high number of parallel tasks. So it's a very, very large scale, and actually being able to scale further just finishes the calculation faster. It does actually not, prohibit it in any way. You have examples of financial risk models. So if anybody is here from a bank, then something like risk systems would run on a platform like this. You've got quant scenarios, which are more research, like quant firms, and you've got Monte Carlo simulations. Then the second column there is around tightly coupled workloads. This tends to be more around fluid dynamics or genomics or healthcare and life sciences kind of workloads, where they need to have this exact required number of compute start before it can do anything. So all of the workers have to come up at the same time, connect to each other basically, because there's a lot of inter-pod communication, and then be able to actually start doing something. But on top of that, which actually makes this even harder, is if you lost 2 pods, or if 2 pods didn't come up, then the rest of the system does not start working. It has to reach that amount of compute. It's called gang scheduling as a term, but ultimately it means that I need to start all of my pods before I can do something useful. And the last one, AI ML has been there a while, but you have to understand, and I say this just as a plug, but AI workloads, your current Gen AI ecosystem of training and inference is exactly these two things. So training is actually a tightly coupled workload, and inference is a loosely coupled workload. Like that's literally how it works. So your magic around Gen AI is just another HPC. There is nothing else to it. So we come to this, toll road. Just taking an example. So you've got loads of cars, and I've seen that here. It seems to happen a lot in Guadalajara. But you've got loads of cars that want to go through a toll. That's your entry point. So say something like API server. If you're trying to schedule a lot of pods, which is I'm trying to run all of these cars through the toll, they will have one contention point. That tends to break your ability to scale. So we will look at how does this happen? How many people in the audience can say they know how scheduling works in Kubernetes? Okay, 0 hands. So I'm glad I put this up. That actually is a oversimplification because there is so many points of communication between the different steps, but also equally the components that are involved in making a pod happen. So when you actually create a deployment, say in Kubernetes, and you run your one pod, a simple deployment of one pod, that still goes through the same cycle as if it's a much larger scale. So when you create a deployment, it has a notion of how many replicas am I going to run. And usually for something like HPC workloads, the instruction, the element that says how many pods do I need is either a scheduling time requirement or it comes from something like metrics. Don't use CPU for your scaling. That's a bad practice. But there is all sorts of other things that you should actually look at. So for example, if you use something like Keda, which is another open source project as part of CNCF, you can watch any metric that is from, say, another service. So if you had a queue of tasks that are coming in to get scheduled for, say, your HPC workload, then that affects the number of pods that are scheduled for that deployment. That basically goes through HPA, tells HPA I need X amount of pods, and then the HPA touches the deployment, increases the number of pods. That affects the replication controller because it actually updates your replica set, and the replication controller sees that and actually starts pods which go into a pending state. And that is not even considering kubelet, it's not even considering the scheduler, it's not even considering etcd. That's purely just the number of pods that are impending. Now this is saved inside your cluster, and then the scheduler says, okay, I need to increase the number of pods that are impending, but then something like, we call it data plane scaling, Carpenter or cluster autoscaler will actually look at that number and then consider how many nodes it has to bring, nodes join, pods start, etc. So again, this is an oversimplification of the scheduling process. There's a lot more going on behind the curtain while this happens. But between the two, they also have different aspects of how they do the scheduling. So Cluster Autoscaler is a project which is as old as Kubernetes. It was the first, say, orchestrator as part of Kubernetes, and actually has an integration with almost every provider there is, on-prem or cloud. And it is using the lowest common denominator API. So every single object, every single API, every single provider that exists out there has a notion of a autoscaling group, something that scales based on that desired replica count. Same as a deployment works. These are actually the same pattern, except that they are for nodes instead of pods. So Cluster Autoscaler works by plugging into the autoscaling group APIs relevant to every CSP, versus AWS actually started Carpenter. It's now a CNCF project, but that works without groups. The reason this is important is that when you make your call to say, I need X amount more nodes, that call goes to the API of the provider that then goes through another cycle to provision your compute capacity. So in addition to your initial delay of provisioning your pods within the cluster, you're waiting for another system that is outside of your control to actually start and bring those nodes up. And obviously, if either of those, or one, depends on which one you install, they are replaceable. So you can't have both. You should have one of them, depends on your workload. But they will actually be also responsible for that scheduling work. So if one of those is like dead, not performing, then your scale up will also suffer. So anything that is basically involved in the system will have consequences on the end-to-end scale system. Then once I've actually, made a request, Carpenter says, okay, I'm going to bring a node up. You're still waiting for one more flow before anything can happen. So now the node actually starts. It has to go through a boot up, your operating system time, your provisioning time from a cloud provider perspective. So when you say I need 5 computers, they actually have to go through booting. They have to pull an image. They have to start in a certain capacity zone where you have available capacity and so on. So all of this is actually responsible for that additional delay on scale as well. Then once the node has booted up, you're in like operating system zone. That stuff, same as on-prem, anywhere else, has to boot. It has to get an IP address. It has to start your kubelet. It has to say, okay, I'm ready, join the cluster. I'm going to pick up pods. Again, all of this affects your end-to-end start time. And then once you've passed everything, just when do the pods actually start scheduling? So then from pending, kubelet says, okay, I'm going to pick those pods. They're on my node. They become available, and you see them as running in Kubernetes. So as you can see, there is a lot of stuff that happens before your workload can actually start, let alone reach a certain scale. So you will have different components that are part of the cluster that are also affected by this. In addition to Class Autoscaler and Carpenter, which, as I said, are responsible for the actual data plane scaling, there are a lot of other things kind of behind the curtains that you don't normally think about that will actually flip over at scale. So if you know Core DNS, for example, that's a in-cluster DNS service, that's a default, that is actually used for every single time a pod or a node wants to join a cluster. It is in use for all of the interpod communications. Anything that happens from a ingress, load balancer service, all of that goes to Core DNS. At large scale, that flips over. Like everything breaks. Like be ready for this to happen at scale. You have other things like metric server, your CNI, you have all of these components that can actually be, if you know what an out-of-memory kill is, they will have a certain amount of requests and limit set. If you're running more things, they will get evicted or killed. And when this happens, your scale stops. So again, this is going to be a iterative process, but ultimately, you will find the next thing that breaks. So now we've had all of our cluster components. They're somewhat fine. Okay, so we say, what's the next thing? Okay, in addition to your daemon set pods, as we said, the stuff that actually runs on the node, think about something like Fluentbit. If it's shipping logs, right? If it has 5 pods to ship logs for, it's a very different resource usage profile than if it's shipping logs for 110. Okay, so you also then have to adjust the daemon sets. But this does come with a caveat, because when you're running daemon sets in all of the nodes, they're consuming actual hardware resources from your node. That just then means that there is less room for that 110 pod. It's actually very rare that I have ever seen someone use 110 pods on one node. That is not a standard process. That's why that limit is kind of set. It's overridable, but it rarely happens that it is. The reason for this is also you could have mixed nodes. You don't necessarily have the same node size. So a smaller node will have room for 10 pods, and a bigger node would have for 50. It's not going to be always 110. And actually, it's a factor of your CPU size. So the 110 is the default limit, but it automatically calculates, the kubelet calculates how many pods it should run or limit on based on the amount of resources that it has on the node. There is also all of the different components on the node. that could get killed or evicted that belong to a daemon set, or say kubelet itself, because you have over-provision capacity on that node. So you could have, for example, a node that has only room for 50 because it does not have resources, but you did not set your requests and limits correctly on your workload. So they could create a situation where you're using more resources from the node that is available, and the kernel basically picks a random process to kill. And it could be the kubelet. And at that point, you've killed your workload as well as the node. So there's all sorts of like metrics and configurations that you have to set to make sure that this does not happen. This is all configurable, but you have to be aware of it. So another thing that is actually really probably the biggest thing that happens to large scale is IP exhaustion. So you would think this does not happen, but it does. So at the scale at which we're talking about, especially if you're running a CNI, which consumes, so CNI is your networking interface controller that actually manages the IP addresses for the pods. If that thing is using the CIDR range of, say, the same flow of your nodes, or your extension of your on-prem CIDR range, depends on your configuration, then you've already exceeded your available IP addresses. So the pods might have all of the physical resources possible, but they don't have an IP to come up, and a pod cannot communicate without an IP. It will actually not come up. So that's then another thing that will break before you've even done anything. And then you'll have your operating system limits. So it could be that you have a kernel setting, like it exists, that controls how many open files a system can have. And at large scale, again, all of your kubelets and containers are just a file in the file system. This is a standard kernel or Linux methodology, ideology, but ultimately it's a file. So you might have, you might hit that open files limit before you've done anything. So I sound like a broken record, but I'm just saying that everything will break and you will try to find what the next thing is. So in that cycle of bottlenecks, when you're doing scale testing, ultimately what you're getting to is, I will try to go to X, whatever that X is, and I will look at the numbers. How do I do that? What's the next thing that is going to break that I need to update to make sure that I can reach that large scale? So it will go through a iterative process of figuring out all of the different things. This is obviously just a list, but it could break differently in your environment. It could be something as simple as your application needs to read from a storage or a database, and your network gets throttled, so your pods cannot communicate. It could be that your storage system, your database, cannot handle that number of clients. Like, all of these things will cause a slowness on the actual startup time of the end-to-end system. And that's before your application has started. The actual application that is being run within an HPC cluster. So you will usually have, for things like machine learning, things like quants and financial risk models, the actual image that is needed to do those calculations tend to be a few gigs. It's not in the 10 megs. So by the time you've pulled those tens of gigs, in addition to them actually kind of DDoSing your container registry, and at the time when you're starting pulling all of those manifests at the same time across a large number of nodes, even when you download, you will still have, say, a storage bottleneck. It could be that they're using different images. So at the same time, you're trying to pull different things. So it will keep breaking. And then your application startup time, if you're running Java, I hope you're not, it will take 2 minutes to start, on top of the actual operating system and image. So again, your pods may say running. If you have health checks they want, if configured correctly, but they may say running, but they're not doing anything yet. So again, the same. And if you're running tightly coupled workloads, as I said, one node, one pod not being there means the system is not doing anything. If you're loosely coupled, you're a bit more flexible, but on a tightly coupled workload, you have to have everything ready. So that's where then it gets even worse. So we have provisioned, we're somewhat running. There's another end to the story. This type of workload tends to run for minutes, hours, depends on what it's doing. But then once it's done, you have to scale down. And guess what? You go through the exact same loop of issues on the way down. Things will not be able to handle the requirement to scale down thousands of nodes at the same time. They will throttle, they will break, and you will actually end up with costs because you have now machines that are running that are not doing anything that you're getting billed for by the second or whatever your billing strategy is. And on top of the actual cost is the API server as well, because all of the node delete options go through etcd, API server, all of the same components that we use for the scale up. So basically, everything is going to break on the way down as well. So with that, I'll show you some graphs. This is a few large-scale tests that I've done for different use cases. So for this one, we're using Cluster Autoscaler, and we're using one single deployment. What that means is we have one application deployment, and that one is being told to go to a certain number. The actual scale-up is somewhat uniform. So I'll just show you because I assume you can't see what that is. The light blue line, which is this, is the number of actual running pods in that deployment. And these 3 things are, that is the kube system proxy, that's the kube system node, and the actual nodes ready. So this is your CNI. As I said, before you have an IP address, you cannot do anything on the node. So you will see that the number of nodes that comes up is actually much higher because at this point, I don't know if this is going to work. At this point, we've already started the operating system, but it needs to start the CNI before any workload happens, or, funny, the node appears as ready. So your node won't show as ready in your Kubernetes cluster, although it's doing something. So then once you've started your CNIs, as you can see, your actual node follows. So those lines are kind of on top of each other because as soon as you've started your node and you have IP addresses, your kube proxy also starts with a node. The reason for that is kube proxy is used for funneling all communications in a Kubernetes cluster. So once you have a node and an IP address, it will be able to show that your communications are passing through. So the node becomes ready, kube proxy is ready, your application is tagging along. Because although you have nodes, it takes some time for that workload to get scheduled, to start running, to be available for running compute. So the actual start of the workload is fairly kind of uniform, but the difference at which the nodes come up is depending on the scale that something like Cluster Autoscaler or Carpenter tells your cloud provider to bring compute for. And it also depends on the speed at which you get compute, because they two don't necessarily match. You could ask for 1,000 nodes, and it takes a while for them to come, versus getting them at the same time. And then here we reach that scale. Everything is ready and running, and then you start your scale down. Again, your pods, from as far as Kubernetes is concerned, it's not a straight line. But eventually we'll say, okay, I'm going to delete my pods. And if you have something like health checking and you handle your sick term and sick kill correctly, then the application will stop in a healthy way. But then it takes a while for your actual nodes to die as well. It's the same exact problem, right? It's a bit wider here, but you'll see that your nodes actually will also go down for a certain time. So in this case, we're running one single application worker pod per node. This is a pattern that some of such scheduling systems use because they want to be able to dynamically allocate compute resources within the node, but they will also be able to handle differing node sizes. So it could be that if you get a smaller node, I'll be able to run 2 processes or 2 threads of whatever the application is, versus if I have a large node, I could do 64. So it is able to control that. But the reason this is important is because as far as Kubernetes is concerned, and as far as that etcd limit that the previous talk was about is concerned, it is dealing with 5,000 pod objects, okay? Now, if we look at another option. So in this case, instead of actually running one single deployment, we're running 5 deployments. 5 copies of the application, but they're being treated, they're being scaled as if they were 5 different deployments. Okay, we're still running 5,000 pods, and each of those individual deployments is going to 1,000 nodes. 1,000 pods. So in this case, you will see that the pattern is different because the different deployments are being scaled at a different time. They have different patterns. They're exact like carbon copies of each other. There's no difference. This is purely the Kube API and the scheduler being able to handle the scale-up operations internally. So there is a metric within the Kubernetes ecosystem called queries per second, QPS. And that QPS controls how often can you call the API server to do something. It could be as simple as kubectl get pods, or it could be a scaling operation. Everything goes through that query per second limit. And that is also actually controlling the speed at which it responds. So if you have a kubectl watch command that is running, you will get an error that will say, go away, because actually the Kube API cannot handle more requests. Funnily enough, also the kubectl command line itself has built-in limits that will say, the logs will show something like, I was slowing down because of client-side limits rather than actually being throttled by the API server. Because a system at this scale needs to have controls and protections at every layer to be able to sustain that. So we actually kind of have a similar scale-up pattern, and you'll see the scale down is kind of exactly the same, but at least you're getting a wider difference at the speed at which the pods are coming from the different deployments. And this could also be a use case of different applications. So you could think about this, how would this be affected or affect, say, a noisy neighbor situation where you might have a cluster that you run for multiple applications for your firm, and they are all using the same API server. Somebody scaling up really fast could actually affect the rest of the system, and it does not let them do whatever they're meant to do. So keep this in mind as well. Now, we have another situation, the magical number, 150,000 pods over 5,000 nodes. So that means we're running about, if this is uniform, about 30 pods per node, not 110. And even in that case, you have to think that we also have daemon sets. We have other parts of the system that are running on those nodes that are actually consuming resources. So if you ran this 5,000 nodes system, 150,000 pods, you come to that 30, which is why it's not 110. It's usually not 110. So with the single deployment, you will see that this line showing, kind of straight, and this is going kind of, evenly up. However, the reason for this is mostly a presentation skew, because the numbers at which we're running, the y-axis here, is tens to hundreds of thousands. So the number of nodes will have some, tiny variances, because eventually it reaches 5,000. But in the large scheme of things, it doesn't show because, it's much smaller than 150. And actually, this kind of scaling takes a lot longer than the 5,000 pods, 5,000 nodes, because every single one of these objects is treated as a separate scheduling operation. It goes through that full cycle that I explained. Every single one of them is treated differently. Versus if you were to start 5,000 pods, you're still running within that limit of etcd, more or less, for nodes. And then the pods are much smaller than the theoretical limits that is posed. Another situation, we have Carpenter, which is the other data plane controller. And you will see it actually does a much better job and aligning your requests for nodes and the applications and the pods running. The reason for this is Carpenter does not use auto-scaling groups. It's what's called a nodeless scaler. So instead of actually calling a cloud provider API to say, give me X nodes, and then the cloud provider API goes through its own cycles of bringing sad nodes up, Carpenter makes a call to an API. It's called EC2 Fleet for AWS, and uses something called instant mode that automatically starts those nodes without needing to go through cycles. So you will see that the actual scaling is much more uniform, and the numbers basically of the nodes running, pods running, are going in somewhat of a step fashion. And as you can see, the further up you go, the space is wider. The reason for this is now we're putting strain on the next part of the system, which is API server, etcd, core DNS, everything else. So when it's here, as you can see, it's fairly uniform. And then at a certain point, it starts just growing up on the time it takes between scale operations. So again, keep in mind that there is limits. And if you ask, how can I go further? Horizontal is the answer. So if you've reached the limit of 150,000 pods in one cluster, you can create another cluster and you can actually scale them separately. The reason for this, and it also aligns with the previous example that I had on multiple deployments, is each different resource type, each different part of the system has a certain limit. So when you're using multiple deployments, the Kube API is treating them separately when scheduling pods. So it actually has a per object type or per object instance limits as well. In this case, when we're actually reaching the actual cluster size limit, we are now scaling horizontally. And this would be my recommendation even for a 50 pod cluster. You know, that's an over simplification, but if you're running in a cloud provider ecosystem, running more clusters is usually not attaching a lot of cost, but it gives you a lot of benefits. So think about, say, your blast radius. If you're killing your API server, like that other guy did before, you're able to have another system that is not affected by this. You could even have the same application run across both clusters, and they're able to scale, separately. Or you could do something like A/B testing. So if anybody here is platform engineering, you know that Kubernetes releases about 3-4 releases a year. Just keeping up with upgrades is a sufficient amount of, toil. So having two clusters that you can upgrade one, take it off, upgrade the other, like doing proper A/B, even if it's testing, is already sufficiently beneficial for having multiple clusters. But that's where also this ability to go further comes. So you've already reached the limits of one cluster, go horizontal. I'm sorry for the plug, but the etcd limitation of 8 gigs is something that is on-prem, the default open source limitation. The cloud providers, AWS included, now have versions of Kubernetes that goes beyond the 8 gigs. So you can actually run Kubernetes clusters with 16 gigs of etcd and above. And that also means that everything else gets scaled. So your QPS, your queries per second limit, also goes up. So the further you scale your cluster, everything else follows. So you're actually able to run larger scale. So we have released an announcement that says you can run a EKS cluster with 100,000 nodes, not pods, 100,000 nodes, way over the 5,000. But that is a use case for ML training, more or less, workloads. Because in those use cases, same as like my 5,000 example before, you will have one pod per node. So you're actually using, or smaller number, not 10, not 50. So you will actually use the resources of that node in full, but you're able to run much wider. And the reason for this is things like, for example, ML training workloads or LLMs, they will require a same cluster. They can't go cross-cluster. You have to have really low node latency or inter-node communication. So the reason is that you want to have all of that workload in one rather than spread across multiple clusters. So in that case, this vertical horizontal might not work. So yeah, there is cases out there that you can run much larger clusters than the 5,000. That's not an actual hardware limitation. It's purely etcd. So with that, some key takeaways. Tests. Like if you're running large-scale compute, do not expect that it will just work. It will not, I promise you. But also on top of it, you need to adjust the defaults. When you set up a standard Kubernetes cluster, regardless of managed service or your own, the defaults that are applied are for generic, medium, average size workloads. They will not work at scale. So you actually need to crank up everything. And again, be mindful that running your, say, cluster components in the same nodes where your workload is might actually kill them. So you're, shooting yourself in the foot. So be mindful of that. You will have regular tests because it could be that the next version of, which I have seen, core DNS, for example, will require more resources with an update. So the new release, like it worked. It worked fine until yesterday. You updated your core DNS and suddenly it breaks. Right. So you have to have a robust system of actually being able to test this end to end. And then, you have to have people. Kubernetes is a multi-layer cake, as we've seen. And being able to actually manage it, even through managed service, still requires the skills, still requires good observability, and being able to see what the issue is. So if you're doing a scale test, you will see things stall, and you won't know why. You won't be able to see why if you don't have good observability in the system and actually being able to see what component failed. But guess what? When you're running that large scale, your kubectl commands also kind of are going to time out. So you won't see necessarily, right? So you have to have those loggers, observability system that ships your metrics somewhere else, that you're able to get that knowledge about the cluster before you kind of falls over. So with that, muchas gracias, and I'll take questions.